Hey everybody, I'm sitting down in my hotel lobby right now. It's pitch black out, and I'm peeking around the corner to see if anyone's actually watching me record this. But I wanted to record this little session to talk about one of the most important concepts in the course, this idea that there are problems out there that computers actually can't solve. The kind of problems we're going to look at are not sort of typical algorithms about solving things about graphs or analyzing strings and whatnot. The problems that we're interested in looking at here are actual problems concerning the formal languages that we've been studying throughout this course. In particular, doing analysis over the machines and the languages we've talked about. One example of that is a problem called acceptance. Given some machine and some input to that machine, does that machine actually accept that input? And we can ask this question for all the machines that we've looked at in this course. DFAs, NFAs, regular expressions, context-free languages, PDAs, and so forth. Another sort of problem we might consider is equality. Given two machines, do they accept the same language? And again, we can do that for all the machines we've talked about. One other sort of question, one you saw on the first exam, is emptiness. Given a machine, is its language empty? And again, we can do that for everything. And it turns out that for all of these machines that I've listed on this slide, they're all Turing decidable languages. That means there's a Turing machine out there that can actually figure out whether these problems are true for particular inputs without going into an infinite loop. And so that seems pretty magical. I want to look at one of these in more detail just so you get a sense that Turing machines can actually do that. And so let's look at perhaps the simplest one of these, the acceptance problem for DFAs. Given a DFA D and then some input W, that pair is inside this language if D accepts W. And our claim is that this is a Turing decidable language, i.e. there's a Turing machine that actually accepts and rejects properly according to the definition of the language. And so our proof is simply constructing said machine. And so we're going to call this machine M. It takes as input this DFA D and input W. And as we've seen in this course, by the time we get to this point, our Turing machine definitions are pretty straightforward. We're not talking about tapes anymore, we're just talking about general implementation strategies. And the implementation strategy for this is really straightforward. First of all, just simply simulate D on input W, and if D accepts W, then accept, otherwise reject. And so this kind of skips over a lot of steps, but captures the essence of what we're doing. We are just simulating the DFA using a Turing machine. And so there's at least two questions that arise that we should ask ourselves. One, can we actually do that? Is it possible to simulate a DFA with a Turing machine? And two, since our Turing machine is supposed to be decidable, does this process of simulation always halt? And we can kind of think back to the DFAs that we hand simulated, and we can convince ourselves that the process always halts. We always take n steps, where n is the length of the input string and no more. And so in that sense, it always halts. And so really the question is, how do we simulate a DFA with a Turing machine? I'm going to go ahead and sketch that out. Recall that the definition of a Turing machine is a 5-tuple consisting of an alphabet, a set of states, a transition function, an initial state, and then a set of final states. The two things that are critical for representing this inside of a Turing machine are, one, the set of states, and it's just some finite set. And so we don't really need to choose any particular representation for it. We can take however we name the states, map them into some finite set of integers, and say those finite set of integers are the states. The most interesting thing is that transition function. We talked a little bit about this when we talked about going from a regex down to a DFA for the purposes of lexing. But the way that we would implement this delta function, we could write kind of a series of functions that act as the delta function. More efficiently, we can write a lookup table where the rows in this table correspond to states, the columns correspond to inputs, and so an entry in this table corresponds to a particular state and a particular input, and the entry corresponds to what we should transition to, or which state we should transition to after seeing that combination of state and input. And so it's just a 2D table, it's finite. We can represent it on our Turing machine tape using roughly n squared space. The space doesn't really matter, but nevertheless we can do it. And furthermore, simulating the DFA just means doing repeated table lookups where the only thing we have to keep track of is the state that we're currently on. And so simulating a DFA is actually very straightforward. Simulating, say, a push-down automata or PDA is slightly more complicated. And remember, the only thing that differs between a PDA and a DFA is the presence of the stack. And so in addition to the state, if we were simulating a PDA, we would actually just keep track of the stack on the tape, which again it's not too onerous to do. So we can believe that we can simulate kind of all these machines using a Turing machine, which is pretty cool. However, there was one combination of machine, or rather one machine that was left out of that previous slide, and that's a Turing machine itself. And so here's the definition of what's called the universal Turing machine. And so ATM is the language of all pairs of Turing machines and inputs such that that Turing machine M actually accepts that input W. Okay? And so we're going to start off with a more simple claim for now, that the language ADFA, or sorry, that's a typo, ATM, is actually Turing recognizable. And so what does that mean? Well, that means that there's a Turing machine out there that recognizes this language. It'll accept all the combinations of Turing machines and inputs such that the Turing machine accepts the input. But on cases where it does not, we might reject or we might go into an infinite loop. And so, again, the proof is just by construction. We have to make a Turing machine that does this. And so this Turing machine we're going to call U for universal is defined as follows, and it looks pretty much like the other definition. 1, take the Turing machine M and then simulate it on input W. If it accepts, then the overall Turing machine U accepts. If it rejects, then reject. And then implicit in that is if M loops, then U is going to loop by default because we're simulating M to completion. And so note that as long as we're able to simulate a Turing machine using or inside of this Turing machine, then we're okay. This is clearly going to accept whenever M accepts W. So that gives us recognizability. It might loop, and that doesn't give us decidability, but that's fine. We only needed recognizability to begin with. And so Alan Turing, in his seminal paper, actually proved that we can actually do this simulation. He crafted the universal Turing machine by hand, had a whole bunch of typos in it, just like this slide, but nevertheless did it, showing that a Turing machine can actually, the universal Turing machine actually exists. The question is, this is only a recognizable machine, or a recognizing machine. Can we build a deciding machine instead, one that actually doesn't go into an infinite loop? And so it turns out that is going to be the problem that an algorithm can't solve, and we're going to prove that. All right? And the way that we're going to prove that is by using a particular proof technique called diagonalization, which we're going to talk about in a minute, but we have to, before we do that, we have to make a brief digression into one other mathematical concept that's important for diagonalization, and that's called countability. And so a countable set is one where we can exhibit a bijection between that set and the natural numbers. And remember, the natural numbers are defined to be 0 and then all the positive integers. And so a bijection is a one-to-one correspondence between these elements. As a concrete example, consider the natural numbers n listed above, and then some set of arbitrary wingdings that PowerPoint happily provided to me. I think a lot of those are like I don't know what those are. Anyways, and so if we want to exhibit a bijection between the two, what we need to do is find some mapping from S to N such that every element of S is mapped onto a unique element on N, and then N likewise has a unique S, or each element in N has a unique S mapped onto it. Okay? And so there are no duplicates, everything is matched up, and so forth. And so let's go ahead and look at some examples of sets that are countable just to get a sense of what this bijection actually looks like. Trivially, the natural numbers themselves are countable. And so if we try to layer the natural numbers on top of each other, we get this very straightforward bijection, where the bijection is just the identity function mapping a number onto itself. Even though the set of integers, which are the natural numbers plus the negative integers, it seems to be larger than the natural numbers, it turns out that the integers are actually countable. The way that we can see that is we have to draw the bijection. And so the bijection looks like this. Conveniently enough, I laid out the definition of the set so that everything sort of lines up correctly. And so we have to actually write down the formula for this bijection. This is the formula right here. And so if you note, looking from left to right, 0 is mapped onto itself. And then we have alternating positive and negative integers going up in absolute value. And so the positive integers are mapped according to the second equation here. If we have a positive integer k, then it's mapped onto the real number, or the natural number rather, 1 plus k minus 1 times 2. You can verify that for 1, 2, 3, and 4, and so forth. The negative numbers are simply mapped onto the absolute value of k times 2. You can verify that there. And so note that this covers all of the integers, and every such integer is mapped onto a unique n, and every n is mapped onto a unique integer. And so because of that, we say that the integers are countable. In Sipser, he also gives an argument that the rational numbers are countable. These are numbers or fractions with whole numbers. And so you can see Sipser for sort of a more elaborate argument of countability. But in any event, we've seen some countable sets. One might ask, are there any sets that aren't countable? And it turns out there is at least one such set. The real numbers aren't countable. And so real numbers are numbers with fractional components that might go off into infinity. And so the question is, how can we possibly map the natural numbers onto these real numbers? And it turns out that we can't do this. The way that we formally argue it is through a proof technique due to Cantor called diagonalization. The way that this proof works, just sketching it out, first we assume that in this particular case the real numbers are countable. This means there has to be a bijection from the real numbers onto the natural numbers. And then we show that there's a real number that exists that is possible to construct but cannot possibly be in this bijection. And this is a contradiction because we assumed that the bijection covered all the real numbers. And so let's go ahead and see how to construct this real number. And so what I have here are the natural numbers on the rows, and then this right column here is going to be the real number that is mapped onto that natural number. And so we really don't know what the mapping is. Our assumptions don't give that to us. And so it's some arbitrary mapping that might look like this, where we just have arbitrary real numbers mapped onto each of the natural numbers. And so our goal is to construct a real number. Oops, excuse me. Apparently, even though it's like 2 o'clock, I still burp. We have to construct a real number such that it can't possibly be in this list. And so how can we do that? Well, we note that because the real numbers stretch off into infinity as far as their decimal expansions are concerned, we can construct this real number k in this manner. Let's look at each digit, or rather, let's look at the first digit of the first natural number, or real number rather, and then let's make the first digit of k be different from it. Let's take the second real number and make the second digit of k be different from it. In this case, I've added 1. And then so forth down the line. And do this for all the real numbers in this list. And so if we note, by doing this, we've made the real number k definitely not equal to each real number in this bijection. And so because of this, it must be the case that k is not actually in the bijection, because it's not equal to any real number inside of it. And that's a contradiction, saying that our bijection captures all the real numbers. And so therefore we can conclude that the real numbers are actually not countable. Okay? And so that's how the diagonalization technique works. We sort of assume that we can draw this correspondence and then construct something that actually can't be in the correspondence. we're going to use this argument to actually show that the universal Turing machine, or rather the acceptance problem for Turing machines, is not Turing decidable. Therefore, there isn't a universal Turing machine that actually decides this language. And so we're going to do this by first assuming that the universal Turing machine is decidable, and then derive a contradiction using the diagonalization method from it. And so let's just call this Turing machine U. It's our universal Turing machine. And so assuming that U exists, it has this behavior. On input M, W, if M accepts the string W, then U accepts. If M does not accept W, which means either M rejects or it loops, which is the kind of split point between being a decider versus a recognizer, then M rejects. Okay, and so implicitly, what this U is taking advantage, or is able to do that our recognizable machine was not able to do, was in the case of a loop, realize that we're in a loop and then reject. Okay, and again, I want to stress the point that this U that I have here, even though it kind of looks like the definition of a Turing machine, is not actually a Turing machine we constructed. It's something that we assumed exists, and this is just kind of stating what its behavior ought to be if it exists. This is going to be the thing that actually is our contradiction. Okay? And so one last thing I need to discuss before I go into the diagonalization proof is a very simple concept. Now that you are very seasoned functional programmers with Racket, is this idea that that second argument to the Turing machine, the universal Turing machine, doesn't have to be just a string. And in fact, because a Turing machine can be written down as a string, just like how a function, say in Racket, can be a first class value, i.e. a lambda, we can pass in a machine as an input to pass to M. And so the most confusing of it, and the most important, is whether or not the Turing machine M will accept itself as input. And so this is a little weird to look at. Looking at it in Racket, it's slightly less horrible. Think of it as we have this lambda that we let bind and call it F. And what we're simply doing is passing F to itself. In most cases, that's probably not going to work, but there are some machines that may look at another Turing machine and do some operations on it. And so that is, in the cases where this makes sense, this was a reasonable thing to do. Okay? And so now our diagonalization proof proceeds as follows. Here's our table, and what we're going to do is we're going to map out the results of the universal Turing machine on pairs of machines, and then passing in machines as input to those other machines. And so the rows represent the machines that we're running. The columns represents the machines that we're passing in as input. And so in this list, we've enumerated all of the Turing machines. And we just kind of labeled them M1, M6 all the way down, and there's an infinite number of Turing machines. And it turns out they're countable as well. The way that we can see that they're countable is if a machine has a finite description, i.e., for example, a program can be written down with a finite amount of text, we can draw a correspondence with that text and the natural number, say, by taking the lexicographical ordering on those strings. And so we have every possible Turing machine represented in this table, and each entry in this table represents whether, say for example, M3 accepts M4 as input in this particular case. And so our goal is to build some sort of contradiction Turing machine, just like how we built a contradiction real number that should be on the list, but for some reason actually cannot be on the list. And so the diagonalization argument comes from taking those diagonals and building a new machine or a new object from it. And so we're going to do the same thing here. Let's define a Turing machine D such that it's going to do kind of the opposite on every diagonal entry in each column. And so reading down the list left to right, what Turing machine D does on M1 is reject, whereas M1, when given itself as input, accepts. For Turing machine M2, it'll reject, because for M2, when passing itself as input, it accepts. For, say, Turing machine M4, it'll accept, because M4, when passed itself as input, rejects, and so forth. And so the contradiction comes from if D is an actual Turing machine, it should exist on this list. And so when we get to the point where we have to ask ourselves what D should actually do when given itself as input, by the definition of D, we're not actually sure what it can do. All right? And so how do we actually define this? This is a good statement of what D ought to do, but we need to have a formal definition of D so that we can assert our contradiction. And so here's the definition of D. It's our contradiction Turing machine. It proceeds pretty straightforwardly. What we're going to do is take that universal Turing machine that we assumed existed, and then on input M, run the universal Turing machine on M, passing M itself as input. And again, this is asking the question, does M actually accept itself as input? And then we're going to do the opposite bit that we saw in the diagonalization diagram. If U accepts, then we're going to reject. If U rejects, then we're going to accept. And so this is the complete definition of D. Assuming that U is an actual Turing machine that we can run, this is a valid Turing machine. Furthermore, it's a deciding Turing machine, assuming U is a decider as well, which is what we assumed to begin with. Okay? And so the final nail in the coffin is this. What happens if we run the universal Turing machine on D, passing D itself as input? And so this is what happens. In the case where the universal Turing machine accepts, if we look at the definition of D, we see that if we pass in or just substitute D for M, we actually do the opposite of accept. When we run the universal Turing machine on D, if the universal Turing machine accepts, we reject. But then we had accepted in that case. Likewise, if the universal Turing machine rejects, then we're supposed to be accepting. However, that case is also the opposite of how D actually behaves. And so in both cases, we arrive at a logical contradiction. It's not an infinite loop. It's not, being wrong. It's just this state cannot possibly exist, given the definitions that we set up. And so because of this logical contradiction, when you have to look at our little trail of all the derivations we've done, to figure out where we actually assumed that something existed. And the only thing that we assumed existed was the existence of that deciding universal Turing machine. And so that actually cannot exist, completing the proof. And so this shows that the acceptance problem for Turing machines is actually not decidable. We can only recognize it. And so this is our first example of a problem that's not actually solvable by an algorithm or a computer. And so this seems like it seems like a sort of theoretical problem. We had to feed in definitions of functions into themselves to be able to arrive at this logical contradiction. But as we'll see next time, this is actually far more than just a theoretical sort of curiosity. This has real ramifications for programs and programming techniques that you use on a daily basis. And so we'll investigate that next time. All right? So I'll see you guys later.